Welcome to this problem walkthrough. In today's session, we'll tackle problem number 1910, remove all occurrences of a substring. This is a classic string manipulation challenge that tests your ability to efficiently remove specific substrings from a given string. Let's dive into the problem and explore some interesting approaches to solve it. In this problem, we are tasked with removing all occurrences of a specific substring, called part, from a given string S. The removal process is iterative, meaning that after you remove one occurrence of part from S, the remaining parts of the string are concatenated together. Then, the new string is checked again to see if it contains any more occurrences of part. This process repeats until there are no more instances of part left in the string. Finally, the function should return the resulting string after all these steps. The input string S and the substring part can both be up to 1,000 characters long, and they consist of lowercase English letters. The output is the modified string after all occurrences of part have been removed. Let's consider the first example to better understand the problem. Here, the input string S is dabkbababk and the substring part is ABC. The goal is to remove every occurrence of ABC from the string. First, we find ABC at index 2 in S, and removing it gives us dababk. Next, we find ABC again at index 4 in the updated string, and removing it results in dab. At this point, there are no more occurrences of ABC, so the process stops, and the final result is dab. This is the string that we return. Now let's look at another example. Here, the input string S is xcib, and the substring part is xy. First, we locate xy at index 4 in the string and remove it, resulting in xcib. Then, we find another xy at index 4 in the updated string and remove it, which gives us xcib. Repeating this process, we remove xy again at index 4 to get xexp. Finally, we remove yet another xy at index 4, leaving us with ub. Now, the string ub contains no more occurrences of xy, so the final result is ub. In the third example, the input string S is foobar, and the substring part is bar. The first occurrence of bar is found at index 3, and removing it gives foobar. Then, we find another bar at index 3 in the updated string and remove it, resulting in foo. At this point, the string foo has no further occurrences of bar, so the final result is foo. This illustrates the iterative nature of the process, where each removal updates the string and the search continues until no more instances of the substring are found. Finally, let's discuss some edge cases to clarify specific scenarios. In the first edge case, if the input string S is ABC and part is also ABC, the entire string is removed, resulting in an empty string as the output. In the second edge case, if S is A and part is B, there are no occurrences of B in A, so the output remains A. In the third edge case, if S is ABA and part is ABA, removing the first occurrence of ABA leaves BA. However, this creates a new occurrence of ABA, which is then removed, leaving just B as the final output. To begin, let's consider a brute force approach. The intuition here is straightforward. We repeatedly search the string S for the substring part, remove it when it's found, and then continue this process until no occurrences are left. This can be implemented using a while loop that checks if part exists in S. If it does, we remove the substring and update S by slicing or using built-in string functions. However, this method has some drawbacks. The time complexity is O, n asterisk m, where n is the length of S and m is the length of part. This is because searching for part in S takes O, n, and we repeat this for every occurrence. Additionally, the space complexity is O, n, as each removal creates a new string. While simple to implement, this approach becomes increasingly inefficient as the size of S grows or when part occurs frequently, due to the repeated slicing and searching operations. Now, to address the inefficiencies of the brute force method, we can use a more optimized, stack-based solution. The idea is to process the string character by character and use a stack to maintain the current valid string. As we iterate through S, we push each character onto the stack. Whenever the top of the stack matches the substring part, we remove those characters from the stack, effectively deleting the substring. This approach has several key advantages. First, by using a stack, we can process the string in a single pass, avoiding the repeated searching and slicing of the brute force method. Second, the stack only holds the necessary characters, which minimizes overhead. The implementation follows these steps: initialize an empty stack, iterate through each character in S while pushing it onto the stack, check if the top of the stack forms the substring part, and remove it if it does. Finally, the stack contains the final result, which we convert back to a string. This method is highly efficient, with a time complexity of O(n), because each character is pushed and popped at most once, and a space complexity of O(n) for the stack. The stack-based solution brings several advantages over the brute force approach. It is much more efficient, as it processes each character exactly once and avoids the repeated slicing and searching operations that make the brute force method slow. This makes it particularly well suited for large strings or cases with frequent occurrences of part. After evaluating both methods, the stack-based solution was chosen as the optimal strategy for this problem. Its key strength lies in its ability to process the string in linear time while keeping the implementation clean and straightforward. Compared to brute force, it eliminates inefficiencies and handles edge cases, like overlapping substrings, naturally. While the brute force method is simpler to code, its inefficiency for larger inputs makes it less practical. The stack-based approach strikes the perfect balance between performance and maintainability, ensuring that the solution is robust, scalable, and easy to understand. This is why it stands out as the best choice for solving this problem effectively. In this problem, we are tasked with repeatedly removing all occurrences of a given substring part from a string S until part no longer exists in S. The final string, after all removals, is what we return. To solve this, we break the process into a series of steps. First, we initialize the key variables, the input string S and the substring part. Then, we create a loop that continues as long as part can still be found in S. Within this loop, we use the find function to search for the starting index of part in S. If find returns -1, it means part is no longer present, and we exit the loop. Otherwise, we proceed to remove the substring by slicing S. Using the starting index, we take the portion of the string before part and concatenate it with the portion after part. This effectively removes the substring and updates S for further processing. Once S is updated, we repeat the process, searching for part, removing it, and updating the string until no occurrences of part remain. At this point, the loop exits, and the final modified string is returned as the output. To see this in action, let's consider an example. Suppose S is dabk and part is ABC. In the first iteration, we locate part at index 2. Removing it involves slicing S into two parts, d before the substring and babk after it. Concatenating these gives us the updated string dabak. This process repeats until no more instances of part are found. In the second iteration, the updated string is dabak, and part is found at index 4. We repeat the removal process, the portion before part is daba, and the portion after is bc. Combining these gives us dabak. Moving to the third iteration, the string is now dabak, and part is found at index 3. After removing it, the string is reduced to dab. At this point, no more occurrences of part remain, so the loop terminates. The final output is the string dab. This example demonstrates the greedy approach we use, where part is removed as soon as it is found, ensuring that no overlapping or hidden occurrences are missed. This greedy removal strategy is effective but has its own efficiency considerations. Each removal involves slicing and concatenating strings, which takes O(n) time for a string of length n. If part occurs k times in S, the total time complexity becomes O(k*n). Additionally, we must account for various edge cases. For example, if S is empty, the output is simply an empty string. If part is empty, no removals occur, and the output remains the original string S. If part does not exist in S at all, the output is also the original string. The algorithm primarily relies on string manipulation and index tracking, making it straightforward to implement. From a space perspective, this algorithm is efficient, requiring O(1) additional space since all operations are performed in place on the string. However, there are opportunities for optimization. For instance, we could use a more efficient substring search algorithm like Knuth-Morris-Pratt, KMP, to reduce the time spent locating part. Another approach could involve lazy evaluation, where we store all removal intervals and construct the final string in one pass, minimizing redundant operations. Finally, here's the Python implementation of the solution. The remove occurrences function uses a simple while loop to repeatedly replace the first occurrence of part in S with an empty string. This continues until part is no longer found, and the resulting string is then returned. For the example input S equals dab babab in part equals ABC, the function correctly outputs dab. This implementation solves the problem by repeatedly removing all occurrences of the substring part from the string S. The main approach is to use Python's while loop combined with the str.replace method. Here is a detailed step-by-step explanation of the code. 1. The function remove occurrences takes two inputs, the string S and the substring part. 2. Inside the function, a while loop is used. The condition for the loop is part in S, which means the loop will keep executing as long as part is found somewhere in S. 3. Within the loop, the str.replace method is called on S. This method replaces all occurrences of part with an empty string, effectively removing part from S. The result of this operation is then assigned back to S. 4. The loop repeats until part is no longer found in S. At this point, the final version of S is returned as the output. This approach is efficient for the problem since it leverages Python's built-in string operations, which are optimized for such use cases. It handles edge cases like when part is not found in S, the loop doesn't run, and the original S is returned. When part overlaps with itself in S, the replace method still works correctly. When S or part is empty, the function behaves as expected. The time complexity of this solution is O, n asterisk m, where n is the length of the string S and m is the length of the substring part. This complexity arises because for each occurrence of part, the replace method scans S and creates a new string. The loop runs until all occurrences of part are removed. The space complexity is O, n, as new strings are created during the replacement process. This is the Java implementation of LeetCode problem number 1910, remove all occurrences of a substring. The logic mirrors the Python implementation, using a while loop to repeatedly remove occurrences of the substring part from the string S until no more occurrences remain. Key differences include the use of Java's string methods like contains and replace, and the structured class definition as required in Java. This solution is concise and achieves the same functionality as the Python version. In this example, we start with the string dap-babap and the substring ABC that we need to remove. Initially, ABC is found within the string, so we begin the process of removing it. The first replacement removes the first occurrence of ABC, resulting in the string dabak. Since ABC is still present, we replace it again, which gives us dabk. Now, ABC is still found in the string, so we repeat the process, and this time the string becomes D. At this point, ABC is no longer in the string, so we can exit the loop. The final output is simply D. This process demonstrates how we iteratively remove all occurrences of the substring until none remain. Now, in this second example, we deal with overlapping substrings. The input string is xc and the substring to remove is xy. Here, xy does exist within the string, so we begin by attempting to replace all its occurrences. However, since xy isn't contiguous in this case and does not directly appear as a complete substring, the replacement operation does not alter the string. This means xc remains unchanged, and since no replacements are made, we reach the end condition immediately. This example highlights how overlapping substrings or substrings that are not directly contiguous may result in no changes to the string, depending on the input. Time complexity is determined by the operations performed in the function. First, we define the lengths of the input strings. Let n be the length of the string S and m be the length of the substring part. The core operation here is the replace method, which scans the string S to locate all occurrences of part. In the worst case, this traversal takes O, n, time. Additionally, if a match is found, it creates a new string excluding part, and the cost of creating this new string is also proportional to the length of S, making it O, n, as well. The function also uses a while loop with the condition while part in S, which involves a substring search. This search takes O, n, time in the worst case. Importantly, the loop iterates as long as part is found in S, and each iteration removes part from S, reducing its length by at least m. This means the loop executes at most n/m iterations in the worst case, depending on how many times part appears in S. Now, combining these observations, the overall time complexity can be analyzed. In each iteration, the in operator and replace method together take n time. Since the loop runs up to n/m times, the total time complexity becomes n/m *n, which simplifies to n²/m. In the best case scenario, if part is not present in S, the loop doesn't run at all, and the only cost is the initial substring search, which is n. On the other hand, the worst case scenario occurs when part is present repeatedly in S and overlaps significantly, forcing the loop to run the maximum number of times and resulting in a time complexity of n²/m. This is the upper bound for the time complexity of this function. The space complexity primarily depends on the memory used during the replace operation and the number of iterations. Each call to replace generates a new string, and in the worst case, the new string is only slightly shorter than the original. This requires n memory for the new string. The old strings are eventually discarded and garbage collected, so the peak memory usage at any given time is determined by the largest string being processed, which is n. Additionally, the algorithm does not use any extra data structures, so the auxiliary space requirement remains constant at 1. Combining these factors, the overall space complexity of the function is n, driven by the memory allocated for the new strings created during each iteration. To put this into perspective, we can compare the current approach to a naive brute force method. A brute force solution would involve iterating through S character by character to locate matches for part and manually reconstructing the string after removing matches. This results in a time complexity of n² in the worst case, as rebuilding the string repeatedly is highly inefficient. By contrast, the current approach leverages the replace method, which optimizes the string reconstruction process. This reduces the time complexity to n²/m, making it more efficient, particularly when m, the length of part, is relatively large. The mathematical justification for the current approach derives from the fact that each iteration involves n operations for substring search and replacement, and the loop runs up to n/m times. Multiplying these factors gives n/m *n, or n²/m. For space complexity, the creation of new strings during each iteration drives the memory usage, which is proportional to the size of the largest string processed, resulting in an overall space complexity of n. One common pitfall when solving this problem is not accounting for overlapping substrings. For instance, take the string AAAA with the substring AA to remove. A naive approach might only remove one AA, leaving AA behind, instead of continuing until the string is empty. To handle this correctly, you need to apply the removal process iteratively until no instances of the substring remain. Another mistake is writing inefficient code, such as using string concatenation inside a loop, which can lead to quadratic or worse time complexity. Instead, opt for more efficient techniques like slicing or leveraging a stack. Additionally, when implementing the iterative removal manually, forgetting to update the string after each step can result in infinite loops, so careful attention is required here. It's also crucial to explicitly test edge cases, such as when the input string is empty, or the substring isn't found at all. Finally, assuming the substring patterns are non-overlapping can lead to incorrect results, especially in scenarios like ABABAB with ABA, where overlaps must be carefully handled to ensure complete removal. In the context of interviews, it's important to fully understand the problem scope. You should clarify whether overlapping substrings need to be removed iteratively and whether performance will be a concern for very long strings. An optimal solution, such as the stack-based approach, is efficient with linear time complexity and straightforward to implement. By pushing characters onto a stack and checking for the substring at the top, you avoid the inefficiencies of repeatedly searching and slicing the string, making it a preferred method. When discussing the solution, highlighting edge cases like empty strings or substrings not present in the input can demonstrate your thoroughness to the interviewer. Additionally, explaining the trade-offs between different approaches is valuable. For example, while a brute force method may be simpler to implement, it becomes impractical for large input sizes due to its inefficiency. This ability to weigh simplicity against performance is a key skill to convey during problem-solving discussions. This problem is closely related to others on LeetCode that involve string manipulation. For example, in problem 1209, you repeatedly remove adjacent duplicate characters with constraints, while problem 1047 is a simpler variation where you only remove adjacent duplicates. Problem 71, on the other hand, involves simplifying Unix-style file paths using stack-based techniques, and problem 316 challenges you to remove duplicate letters to achieve the smallest lexicographical order, adding another layer of complexity. Alternative approaches to solving this problem also come with trade-offs. A brute force solution, while straightforward, is inefficient for larger inputs as it relies on repeatedly searching and slicing, leading to quadratic or worse time complexity. A stack-based approach, however, is both efficient and naturally handles overlapping substrings, making it a strong candidate for this problem. The two-pointer technique is another option that can be efficient but may feel less intuitive compared to stacks. Finally, a regex-based solution can be concise but is often slower and less transparent, especially when debugging edge cases. Choosing the right approach depends on the constraints and goals of the problem at hand. Great job! In this session, we explored how to solve problem number 1910 by removing all occurrences of a substring efficiently. Remember, string manipulation is a core skill that comes up often in coding interviews, so practicing problems like this is invaluable. Thanks for watching, and don't forget to like, subscribe, and stay tuned for more problem-solving walkthroughs. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!